Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual landscape of 1909, physics confronted a profound and unsettling paradox, the turn of the century, and witnessed a triumph of empirical curve fitting in Max Planck's law for black body radiation. The formula worked with astonishing precision, yet its derivation rested on a foundation of what Planck himself called an act of desperation. The physical meaning of his own mathematics was shrouded in ambiguity. The core of the problem concerned the location of the quantum discontinuity, was the strange discreteness, the quantization of energy, a peculiar property of the material oscillators within the cavity walls, as Planck's original derivation suggested, or was it an intrinsic, revolutionary feature of electromagnetic radiation itself, as Albert Einstein had audaciously proposed with his light quantum hypothesis in 1905. The field required an intervention, an act of supreme analytical hygiene to untangle assumption from consequence. Paul Ehrenfest, a physicist steeped in the rigorous traditions of Viennese theoretical physics, provided precisely this intervention. His 1909 paper, bearing a direct title on the physical meaning of the quantum theory's formulae, was a masterpiece of conceptual clarification. Ehrenfest brought a powerful analytical tool to the problem, one inherited directly from his mentor, the great Ludwig Boltzmann. He wielded the foundational principles of statistical mechanics as a scalpel to dissect the logical structure of Planck's work. His objective was surgical to isolate the absolute minimal set of assumptions necessary to recover the empirically correct radiation law. He sought the irreducible quantum postulate. Ehrenfest's argument proceeded with relentless logic, beginning with the bedrock of Boltzmann's statistical interpretation of thermodynamics. He invoked the famous principle S equals k logarithm of W, where S represents entropy, k is Boltzmann's constant, and W signifies the number of distinct microstates, or compactions, corresponding to a given macroscopic state. This principle connects the macroscopic, observable quantity of entropy to the microscopic world of probabilistic arrangements. He first applied this machinery to the classical picture, assuming that the energy within the black body cavity could be distributed continuously among the various electromagnetic modes. Following the established methods of Lord Rayleigh and James Jeans, Ehrenfest demonstrated how this assumption of a continuous energy spectrum leads inexorably to a specific formula for the energy density. The result was the Rayleigh-Jeans law, a formula that, while successful at low frequencies, predicted an infinite energy output at high frequencies. This outcome, the infamous ultraviolet catastrophe, represented a spectacular failure of classical physics to describe reality. The derivation was sound, therefore. The core premise of continuous energy had to be flawed. The classical continuum offered a path only to absurdity. Having cleared the conceptual ground, Ehrenfest turned to Planck's formula. His central insight was a pivotal shift in perspective. He argued that the essential quantum element lay in the statistical treatment of energy itself. The physical nature of the supposed material resonators became a secondary detail. The crucial step was to treat the total electromagnetic energy E within the cavity as being composed of a finite number of discrete, indivisible energy packets. Each packet possessed an energy epsilon, defined as Planck's constant h multiplied by a frequency nu. The problem then transformed into a purely combinatorial one. How many ways can one distribute p such identical energy packets, where p equals the total energy E divided by epsilon, among n distinct oscillator modes within the cavity? By employing a specific combinatorial technique for counting the arrangements of these indistinguishable energy quanta among the modes, Ehrenfest successfully derived Planck's radiation law from first principles. His proof made it clear that the result hinged entirely on this statistical procedure. The formula emerged directly from the assumption that energy comes in discrete units and from the particular method of counting how those units can be arranged. This was the true quantum hypothesis. In its most distilled form, it was a postulate about the statistical behavior of energy, a new rule for the grammar of nature's accounting. Ehrenfest's analysis revealed that Planck had, perhaps without fully internalizing its revolutionary implication, stumbled upon a new form of statistics. The quantization was a property of the radiation field's energy states, and its consequences were manifest through a novel combinatorial logic. His paper established, with irrefutable clarity, that the path from Boltzmann's classical statistics to Planck's empirical law required crossing a deep conceptual chasm, a chasm defined by the discreteness of energy and the unique way it must be counted. The incisive clarity of Ehrenfest's analysis found its most receptive and consequential audience in Albert Einstein. For Einstein, who had proposed his own audacious light quantum hypothesis in 1905, Ehrenfest's paper was a profound vindication. It provided powerful, independent confirmation that the discreteness of energy was the essential ingredient within Planck's formula. by demonstrating that the entire derivation depended solely on the statistical treatment of these energy elements. Ehrenfest had liberated the quantum concept from the scaffolding of fictitious mechanical oscillators. Einstein's light quanta were thereby elevated from a useful, albeit radical, heuristic device to a conclusion of compelling logical force. If the statistics of discrete energy packets yielded the correct law for blackbody radiation, then one had to take the physical reality of these packets seriously. The paper armed Einstein with a rigorous argument. The quantum nature of light was a direct consequence of the statistical mechanics required to explain empirical observation. This intellectual clarification forged a direct, traceable lineage to one of the next great leaps in quantum theory. The seeds of Ehrenfest's reasoning came to full fruition 15 years later in the hands of Satyendranath Bose. In 1924, Bose, then a radio in physics at the University of Dhaka, sent a short manuscript to Einstein for his consideration. In it, Bose accomplished something remarkable. He derived Planck's radiation law from first principles, using a novel statistical method that built upon the very foundation Ehrenfest had exposed. Bose took Ehrenfest's conclusion as his starting premise. He dispensed entirely with any lingering connection to classical electrodynamics and focused exclusively on the statistical mechanics of light quanta, which he treated as a gas of particles. His pivotal insight was to treat these photons as fundamentally and absolutely indistinguishable. Bose's method involved partitioning a system's phase space into cells of volume h cubed, where h is Planck's constant, and then counting the number of ways photons could be distributed among these cells. Critically, he considered two arrangements identical if they merely swapped one photon for another. This was a radical departure from the classical counting of Maxwell and Boltzmann, where every particle is a distinct, nameable entity. From this single, powerful postulate of indistinguishability, the entire Planck distribution law emerged with breathtaking simplicity. Einstein immediately grasped the paper's profundity, translated it into German, and arranged for its publication. He then extended Bose's method to a gas of material particles, developing the theoretical framework we now call Bose-Einstein statistics. The very existence of this new statistical class, governing particles that we call bosons, is the ultimate fulfillment of the logical path Ehrenfest first illuminated in 1909. He had identified the counting method as the crux of the matter. Bose invented the correct counting method by embracing its deepest physical implication. The enduring legacy of Ehrenfest's paper extends even further, providing a conceptual antecedent to the architecture of modern physics. His insistence on understanding the quantization of the radiation field's energy states prefigures the central idea of quantum field theory. In the framework of QFD, the universe's fundamental constituents are pervasive. Underlying fields, particles, such as photons or electrons, are understood as localized excitations of these fields, quanta of field energy and momentum. Ehrenfest's careful separation of the quantum postulate from any specific mechanical model helped steer physics toward this more abstract and powerful picture. He focused attention on the properties of the electromagnetic field itself, viewing quantization as a rule governing its allowable energy states. This perspective is a direct intellectual precursor to the canonical quantization procedures of QFD, where classical fields are promoted to quantum operators, and particles emerge as the discrete manifestations of their activity. This focus on the statistical behavior of fundamental entities has become a cornerstone of contemporary science. The statistical rules championed by Ehrenfest and perfected by Bose are indispensable for describing a vast range of physical phenomena. The operation of a laser, for instance, depends on the process of stimulated emission, a behavior intrinsic to photons and other bosons that encourages them to occupy the same quantum state, creating a coherent beam of light. The bizarre and frictionless flow of superfluid helium-4 below a critical temperature is a macroscopic quantum phenomenon, a liquid behaving according to the collective dictates of Bose-Einstein statistics. Perhaps the most spectacular confirmation is the creation of Bose-Einstein condensates, exotic states of matter where millions of atoms, cooled to near absolute zero, coalesce into a single quantum state, behaving as one giant superatom governed by Bose's Ultimately, Paul Ehrenfest's 1909 paper stands as a defining act of conceptual hygiene in the annals of science. It introduced few new physical results. Its immense power resided elsewhere. It was an exercise in intellectual purification, a relentless application of logical rigor that scraped away the confusing and extraneous elements of Planck's work to reveal the pristine, revolutionary core beneath. By asking what was truly essential to the quantum hypothesis, Ehrenfest compelled his contemporaries to face its strange implications head-on. He demonstrated that a physicist's most potent tool is sometimes a question, precisely formulated. His work corrected the trajectory of a nascent revolution, ensuring it proceeded from a secure logical footing and revealing the profound truth that sometimes the deepest discoveries come from understanding the true meaning of the equations we already possess.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.